Okay. Hello everyone, I'm Matteo Maccanti. I'm a telecommunication engineer and I'm part of the data science team of MooSolution. MooSolution is a company working in the field of structural health monitoring, smart structural health monitoring. Today I'm going to present you one of our main projects, the Modal Tracking with LoRaWAN wireless system based on automatic cloud algorithms. So this is the flow of my presentation. Let's go to the first chapter. Why do we choose LoRaWAN? LoRaWAN is a wireless communication protocol that has three main advantages compared to other technology as Wi-Fi, Bluetooth, and so on. The first one is the wide coverage range. LoRaWAN cover up to a few kilometers in the best case, for example, when sensors and gateways are in line of sight. The second one is the low power consumption. That is an important feature when we are going to do a long period monitoring and when sensors are powered by batteries. The third is the low cost hardware. The LoRaWAN hardware is very cheap and it has low maintenance cost. This is our system, starting from the bottom, from the sensors. The sensors are installed on the structure. They acquire data and they send the data with LoRaWAN to the gateways. The gateways are the transceiver of the system and they communicate with the network server. Network server is the brain of the whole system. It is able to manage all the operation, for example, authorization and verification procedure. It route uplink and downlink messages and so on. The last, on the top, we have the services, the application server. In particular, we have developed a cloud platform where it's possible to visualize data, manage the network, and perform data analysis. But we can also export our sensor data via MQTT or FTP or APIs to the customer services, private customer services. Move develop many kind of sensors, but today I will focus only on accelerometer SHM that has been developed especially for the modal analysis. Here we have the main feature of this sensor. I would like to highlight one of these. That is the wireless synchronization with an high accuracy synchronization up to 500 microseconds. This is a great achievement in the wireless communication sensor. LoRaWAN also has two main disadvantages. The first one is the low data rate. So we overcome this problem with a huge data compression. We use a lossless bitwise compression on board on the sensor, and it can reduce the dimension of the acquisition up to 50%. The second problem is the packet loss, the packet collision on air. So to avoid this problem, we adopt listen before talk algorithm. So with this algorithm, the sensors listen the channel before they are going to send their data, and only if the channel is free, they are going to transmit. If the channel is busy, they are going to switch to another channel. Automated OMA is one of the most recent topic of the research. The main advantage are here illustrated. We would like to reduce the operator intervention. We would like to reduce the need of a skilled professional in case of continuous monitoring and in long period monitoring. We improve the reliability of model analysis, and we would like to generate clearer results. So, to do this, we have developed an AOMA algorithm that has these characteristics. It's fully integrated on cloud, it's fully automated, it's scalable, flexible, and reliable. It has three main phases: the data processing, the training, and the tracking. So let's go to the first one, the data processing. Every day of the monitoring period, we are going to perform this operation. The first one is the pre-processing. All the acceleration data are filtered with a bandpass filter to discard all the noise components that are not needed for the analysis, and all the events with huge acceleration peaks to EV traffics are discarded. So after that, we have the data stationarizing block. In this block, we are going to do a signal power normalization to be sure that the signal entering on the FDD technique is more or less similar to white noise. In the third step, we have the FDD technique, from which it's possible to extrapolate the model frequencies and model shape. From the first eigenvalue, as we can see in the figure, we apply the automatic peaking, and we, for example, in this example, we identify 4 peaks. Each peaks are associated to a model shape extrapolated from the eigenvectors. So at the end of the processing, we have many points, many pairs. The first value is the frequency, and the second is the model shape. After that, we have the training period. So after calculating and collecting a prefixed number of points, the training period starts. So training is the process for recognizing and classifying the vibrational mode. So we take the point cloud. Each point is associated to a frequency value and a model shape value. And we start with the training. The first step is the outlier removal. So all the points that are that have many difference from from others are discarded with the DB-scan clustering previously performed on modal frequencies and then on modal shapes. After that, we have to correctly choose the starting cluster for our classification algorithm, and we do this with a Monte Carlo simulation, and then we go to the classification of variational mode. We perform with this classification with distance-based hierarchical clustering, and we use two distances, the frequency one and the modal shape, the shape one. After that, then we have the labels. Labels are used to characterize one specific mode, vibrational mode. And these are very important for the tracking period, because these are used with as reference mode, and we are going to update this reference mode based on the new points associated to the trace. The points it's associated only if the following conditions are simultaneously met. I finish with a case study. This is a real case study near Florence. We have installed here 17 accelerometer, and this is our results. So I summarize here in the best way, but you can find all the results in the paper. On the left, we are the modal frequencies time series, and on the right, we have the corresponding average modal shapes. But in reality, each point of the trace has one modal shape associated. So this is only an average modal shape of the trace, so of the all the trace. So here we have the conclusion. The purpose is is to present a new wireless monitoring system characterized by LoRaWAN technology adopted to SHM purpose, cloud-based data storage and processing, automated approach, fully automated algorithm performing identification and monitoring of vibrational mode. Thanks for the attention.